All right, you guys. We're going to do a review of Newton's laws. Review of Newton. Right? You know, there's actually, I think, a computer named Newton once. I'm not sure. I think they made one. It was weird. They called it a Newton. No, it's like a little bitty touchscreen type pad. I think IBM made it. Newton, they call it. What a weird name. I mean, not really that weird, but sort of like a cookie. So anyway, we're going to do a review of Newton's laws. So first, remember that's inertia. I'm going to try to keep this down to about 10 minutes. And that's resistance. There's an I in there. There's an S in there too. Resistance to change. So what do I mean by that? Or what do they mean by that? Galileo and Newton. Galileo was the first person to come up with this sort of idea that it would keep moving. Newton capitalized on it, made it his own. And is that if you have a lot of mass is a measurement of inertia, then you have a lot of inertia. So that means it would take a larger force to get you going, or it would take a larger force to move you or change you. But it doesn't matter about the larger force or smaller force. What it basically stands for is that if you're an object and you're moving in this direction and there's no other outside forces acting on you, you're going to continue moving in that direction forever, unless all of a sudden here comes an outside force acts on you, and that would cause you to change your inertia. And so that's all that they mean when they talk about inertia in that respect. So that's pretty simple. So then the second law was the sort of the biggest part, and that was the summation of forces equal ma. And this is where we get into the vector nature, that force is a vector. And please don't forget that a Newton is the same as a kilogram times a meter per second squared. And 1 Newton would be the amount of force necessary to accelerate 1 kilogram at 1 meter per second squared. So that's pretty simple. And then we use that law to expand upon it. We did a version where we talked about the weight. Remember, I really wanted to get you understanding the weight of an object. It is equal to its mass times the acceleration due to gravity here on Earth. And remember, little g is not gravity, it's acceleration due to gravity. And if you take a person's mass and multiply it by their weight, by acceleration due to gravity, you end up having the weight in newtons, because if you look, that's kilograms times meters per second squared, so it's the same units. And all forces are measured in newtons. So weight, it is a vector, and it's pointing straight down, and that got us to free body diagrams, where we said, oh, well, that means that if you're standing on the Earth, then there is a force acting on you in that direction, and then the Earth, of course, would be the equal and opposite force, leading us to Newton's third law of the action-reaction. And by reaction and action, I'm referring to forces. That if you push on something, it will push back equally and opposite. If you pull on something, it will pull back equally and opposite. You can't push without getting pushed. You can't bump without getting bumped. But what makes the difference then is that you look at this in a different perspective. You take it from a different point of view. You say F is, if you put an F on something, then you'll get a negative F back. But if you look at it from this perspective, MA, then you'll get another MA back, a negative one. And then if you look at it even further, but then you say, well, wait a minute, what about if I push on the wall? Well, then you say, oh, big M, little bitty A, and then U, relative to the school, like the AC floor, a 200 building, U, little bitty M, and then big A, right? So but it doesn't matter that they're different. Their forces are the same. And that's what Newton was trying to say, is that the mass times acceleration of one body will be equal to the mass times the acceleration of the other body, which mass times acceleration in this case is force. So there's getting quickly through that's sort of fun to watch, and quickly through the three laws there. And then we start talking about application of this. So now we have a book. A book's being pulled along with a force F, and it has a normal force, F normal. Remember that normal force is only due to when you have a contact with the surface, and it's perpendicular to the surface. and then you have mg downward, and then let's just say that you have a frictional force backwards. So this, and we call this force applied. So then I ask you to please do your summation of forces along the x, and you say, okay, summation of forces along the x. Now you use this, what do you call it, free body diagram. Sorry about that. So I'm trying to see if I can get a highlighter while I'm talking to you. There we go. And with a free body diagram, although it's not going to do it, I don't want to waste too much of your time. There we go. Highlighter, okay. There, oh, I did highlight it. Okay, there we go. And you say, oh, there's my x, so I'm going to work with my x. So here we go. Summation of forces along the x. FA minus FF. And then we've set that equal to MA. Now remember, if it's equal to 0, then it's not then the sum of the forces would equal 0. So I'm gonna write that here in just a minute. So summation of forces along the y, and so if we do summation of forces along the y, we say Fn minus mg equal 0, because we know it's not accelerated in that direction. And here I'm just going to see if by chance I can finally get that, maybe use a different color highlighter. So there's our y-axis, and so you use that free body diagram to help you sum your forces along both cases. And then you're going to ask yourself a question when you do these. The summation of forces, if they're equal to 0, then A equal 0. By A, I mean acceleration. And therefore, that's the little symbol for therefore, it's at rest or constant velocity. Okay? So those are the questions you have to ask when I give you this tomorrow. After you sum your forces. So here and here are very important to pay attention to. There's two cases in there. So the other thing that Newton's 3 laws encounters is, for instance, what if it was a book sliding to rest? So that's a very common question to give. So we have mg and force normal, and then the book is sliding to rest. So that means there's nothing else pushing on it. So the only thing, there's nothing pushing it forward anymore to the right. Let's say the book is sliding to the right, but there's friction slowing it down, and that force is pushing to the left. So here, if you did your summation of forces along the x-axis, then you would clearly see that there's only one force, and that must be the force that's causing it to accelerate. And then if you did the summation of forces along the y, which I'm going to put over here, then you clearly see that that's Fn minus mg equals 0. Now if you take this and you say, but wait, he told us that force of friction equals mu force normal, and so if I substitute in mu force normal for force of friction, I get mu force normal equal ma. And then I say, oh, but wait, over here, Fn equal mg. So if he gives me the mass of this thing, he is also giving me the normal force for this particular problem. So whatever this thing may be. And so that means I have the normal force. So, or I could just say, well, in that case, if Fn equal mg, I could just put in mu mg equal ma. And notice that you don't even need the mass, because the mass cancels out. And heck, you could now find the acceleration from here if I gave you mu and g, or if I gave you a and g, you could find the coefficient of friction. Remember, that's the coefficient of friction. And that is the ratio of the force of friction to the normal force. All right? Trying to think of anything else I just want to mention. Just take your time, put together a good diagram, write your forces based upon the diagram, and then solve for it with no numbers in it, and then plug in the numbers at the end, and you'll be good to go. Okay? All right. I'm going to stop because it's 9 minutes and 50 seconds.